This gray dot represents the particle that gives everything mass, the Higgs boson. It is a part of a group of subatomic particles called bosons. There are 4 other bosons, called the gauge bosons. First, you have the photon, which is responsible for light and many things within electromagnetic forces. Then you have the W and Z bosons. Finally, you have the gluon. These 4 bosons are responsible for 3 of the 4 fundamental forces of the universe. Let's explore them. This is a proton. It has a positive charge. This is a neutron. It has no charge. Together they make up the nucleus of an atom. They are atomic particles. Now, these atomic particles are made up of subatomic particles, this time called quarks. There are 6 types of quarks: up, down, top, bottom, strange, and charm. Different combinations of these will create different particles. For example, a proton is composed of 2 up quarks, each with a charge of positive 2/3, and 1 down quark with a charge of negative 1/3. Together, if you add that all up, it adds to positive 1, which is why a proton has a charge of +1. Orbiting around the nucleus is the electron. It has a negative charge, and it itself is a subatomic particle. It belongs to a group of subatomic particles called leptons. Electrons, muons, and tauons, each with a corresponding neutrino. Now, physics tells us that opposite charges attract each other like the north and south faces on a magnet, and that like charges repel. So how does the nucleus of an atom, which only consists of the positively charged protons and the neutral neutrons, stay together? It would require quite the force. A strong force, you could say. This is where the gluon comes back in. Between quarks are gluons, which act as a force carrier for the strong force. In fact, all bosons act as force carriers. The W and Z bosons are both force carriers for the weak force, which both controls gamma and beta radiation, and the weak force, which is what binds electrons in atoms. Unlike the strong force, the weak force can be quite easily overcome, which allows bonds such as ionic bonds to form between atoms. If you try to overcome the strong force, then you would get a nuclear reaction, which, in case you didn't know, is how you create a nuclear bomb. Lastly, photons, and also leptons as a group, are the force carriers for the electromagnetic force. Photons are how the electromagnetic force and radiation is expressed within E&M. Now, the only force not explained with this model, you could call it a standard model actually, is gravity. Some physicists think that there is another boson to act as a force carrier for gravity somewhere out there, the graviton, which, while not proved, does make sense hypothetically. And while all these are important, electromagnetism is by far the most prevalent of the 4 forces within this video, which means our first topic is electromagnetism and electrodynamics. A charge is an electric force on an object that exists when that object is in an electromagnetic field. Earlier, I told you that now, physics tells us that opposite charges attract each other like the north and south faces on a magnet, and that like charges repel. How do we know that? Well, there was this guy named Charles Augustin de Coulomb, and through some cool physics, he created Coulomb's law, which is used to measure the strength of the electrostatic force between 2 charged objects. For example, if we have one object with a charge of -2 microcoulombs, and another 4 centimeters away with a charge of 6 microcoulombs, then plugging in our equation gets us about 67.47 newtons worth of force. Okay, another example. Let's let Q1, which is the first charge of the first object, equal 5.972 microcoulombs, and Q2 equals 0.07347 microcoulombs. Let's say that they're placed roughly 384,000 kilometers away from each other. What's the electrostatic force between them? I'll give you a second. Is this a stupid question? Yes. But if you change microcoulombs to kilograms and switch out Coulomb's constant for the gravitational constant, you suddenly get the gravitational force equation. And you find that the force between the 2 objects, which happen to be the rough mass of the Earth and the Moon, is about 1.98 times 10 to the 20th newtons. While we're here, I'd like to throw in this diagram of circular motion. These equations describe the relationships between different aspects of circular motion. Consider circular motion mentioned. Okay, back to electrons. When electrons move, or just exist at all really, they create an electric field, which is just the range in which force with another charge can be observed. In a wire, electrons move across it due to the electric field created when voltage is applied to the wire. Voltage itself is just the difference in potential electric energy, so that checks out. However, when traveling in a wire, electrons will meet resistance by the material of that wire. The material itself has something called resistivity, calculated with this formula, and the total resistance the electrons will encounter within the wire can be calculated with this formula. You can also calculate the resistance by dividing the voltage by the current, which is called Ohm's law. So, if you have 4 voltage worths, or 4 volts, and a current of 2.1 amps, as well as knowing the cross-sectional area is about 2.46 times 10 to the negative 7 meters, and knowing the length of the wire is 0.1 meters, then what is the resistance and the resistivity of the wire? Well, resistivity is just voltage over current, so it equals 1.9 ohms, represented by omega. Then, using that in our resistivity formula, we get the resistivity of the wire, which is about 4.67 times 10 to the negative 6 ohms per meter. We can connect wires with many electrical components such as transistors, resistors, batteries, light bulbs, and many more to create complex electrical circuits. And with those circuits, we can utilize electricity to create many things. There are many circuits, but there are 2 specific ones I will mention, series and parallel circuits, which are both different types of DC circuits. Series circuits take a single path through any resistance, and so the resistance of that circuit is simply adding up the resistance of the whole path. Parallel circuits, however, have multiple paths for electrons to use, and so the total resistance is calculated by adding the reciprocal of each resistance section in the circuit. I mean, that's all nice, but when you run electrons through a wire, something else is created. Heat. That means it's time to talk about thermodynamics. Energy cannot be created nor destroyed. That law, part of the 3 laws of thermodynamics, simply states that the total energy of a system remains constant no matter the form it takes. The other laws are as follows. The zeroth law, because physicists can't name anything right, states that if 2 bodies are in thermal equilibrium with a third, then those 2 original bodies are also in equilibrium. Essentially, any bodies touching each other given enough time will balance out to a thermal equilibrium between all of them. The first law of thermodynamics is the conservation of energy, which, if you missed it, is your fault honestly, and now you have to go back to rewatch it. The second law of thermodynamics defines that the entropy of a system and the universe increases with every interaction. Entropy itself can be seen as the amount of disorder in the universe, and with every single interaction between all atoms and particles, it increases. Entropy, like time, is irreversible to our current knowledge, and thus marks a way to keep track of the progression of all things. The third law of thermodynamics states that the entropy of a system at 0 Kelvin, which means it's a system without any energy at all, is near to or at 0. This further confirms how entropy can only increase as you cannot have negative entropy, since then you would have negative Kelvin, which would be the same thing as negative energy, which cannot exist. This is a good opportunity to quickly touch on internal energy, which is just the amount of energy within something. This is often observed as the amount of vibration or movement that the molecules of something are being observed to have. When something has no movement, when we can say that the internal energy is at 0 joules, and therefore the temperature has to be at absolute 0, or, as we said earlier, 0 Kelvin. We use joules as our unit of energy. An equation such as Q equals mc delta T describe the amount of thermal work done in a system with a specific heat capacity, change in temperature, and mass. For example, using Q equals mc delta T, if we have 50 grams of water increased by a temperature of 20 degrees Kelvin, then what is the amount of energy that the water gained? If you struggled on that, that's because you don't have C, or the specific heat capacity of water. The specific heat capacity is essentially the ability of a substance, such as water, to retain heat. This value can be calculated if we have joules already, but since we don't, I'll just tell you that it's roughly 4.18. Now, if we multiply all of that, we get approximately 4,180 joules of energy gained, or 4.18 kilojoules. Anytime you're finding the joules of something, then you are finding the thermal work done. Now, heat can be transferred in many different ways. The first one is conduction, which is the physical contact with 2 or more bodies. As the 0th law of thermodynamics states, after enough time, those 2 bodies or more will be at the same temperature. Another type of heat transfer is convection, which is the heat transfer carried out in liquids and gases. Another thing I want to quickly note is latent heat. Latent heat is the heat absorbed during a phase change, which is like going from a solid to a liquid to a gas, etc. As a substance changes from one state to another, the heat will remain at the same temperature until all of that substance has been converted into this new phase. This can be seen in this graph on screen, where there are plateaus during the phase changes, which represents the latent heat. Finally, you have radiation, which is the heat transfer carried out by particles such as the previously discussed photons and by other radiation waves. Wait, what the hell is a wave? Take a photon. As it moves, it oscillates up and down in a wave. The distance from the midpoint of this wave to the minimum or maximum is the amplitude, and the time it takes for the wave to make one full oscillation, or travel one wavelength, is the period of the wave. The frequency of the wave is the amount of periods that will happen within 1 second, which is measured in hertz, which is just inverse seconds. Waves can spread out very easily, and it's a property that pretty much all waves have in common. Optics is the study of light and how it operates, and physical optics takes specific looks at several things, but most importantly for this video, diffraction. In the famous double slit experiment, we can observe that since light is a wave, it spreads out from the slit after passing through. When it comes to diffraction, when the light is aimed at something, such as a string, then the light is diffracted among a surface in distinct maximums and minimums, in a repeating pattern. By using trigonometry, we can find that half of the inverse tangent of the triangle made from the string to the center of the light to the second order maxima is the scattering angle. Then by plugging it into this formula, we can find the scattering vector Q. Here's an example problem. If we have a laser with a wavelength of 532 nanometers hitting a string, which is 165 meters away from a surface that the light will project on, and the distance from the center of the light to the second order maxima is 2 centimeters, then what is the scattering vector of the laser? Well, by using an inverse tangent, we can get that delta theta is about 44.83 degrees. Then, by plugging in everything into our formula for Q, we get that the scattering vector is about 16,650,000 per nanometer. When light passes through a vacuum, its speed is equal to c, which is about 299 million meters per second. However, when it enters a different medium, that speed changes. If it enters a prism, for example, the light will slow down and refract. Refraction is a part of geometric optics. In this diagram, light is in one medium, but when it enters another, it is refracted. By measuring the angle of incidence and the angle of reflection, you can use the incident and refracted index to find one of the 4 unknowns of the 4 variables previously mentioned. Now, there's another type of wave called a standing wave. Essentially, it's a wave that is stationary or that has been superimposed with a wave that have the same amplitude and frequency, just moving in the opposite direction. The points in which the amplitude are 0 are called nodes, and when it reaches its maximum or minimum, those are called antinodes. You can see standing waves that come in many forms, but most commonly you will see them on instruments. As on string instruments, the string stays in place as it oscillates instead of moving. Speaking of sound waves are another type of wave. In order for sound waves to exist, they need a medium to travel through, and on Earth that medium is almost always air. The pressure and density of these air waves created by sound waves transmit the sound into our ears to be processed by our nerves and eardrums. Finally, for waves, I'm going to briefly touch on simple harmonic motion. In short, simple harmonic motion is the linear restoring force to a fixed equilibrium point. With Hooke's law, we can find that the force, or magnitude, is equal to the x-axis on a force graph, which would just be x, multiplied by negative k, with k representing the spring constant. Hooke's law can be used to measure the force in springs, pendulums, and many other types of systems using simple harmonic motion. K is also not a specific constant, but it is constant to whatever type of spring or material you are using. Now, all of this probably makes you wonder who the hell had time to go and discover all of this. Well, I guess it's time for a very quick overview of modern physics. Okay? 3, 2, 1, go. While physicists such as Galileo and Kepler came before him, Isaac Newton is by far the most important physicist. Not only did he create the laws of motion, but he also invented calculus as a field, contributed heavily to optics, and single-handedly revolutionized physics and mathematics by his mid-20s. Quite a big deal. Following him, there were many smaller advancements made by people like Lagrange and Maxwell, like those pertaining to theoretical physics and electrodynamics respectively. However, it wasn't until the late 19th and early 20th century where many more massive breakthroughs were made. Not only did we discover the parts of the atom, the proton, neutron, and electron, but we also discovered how to make atoms, and more significantly, how to split them. If you remember from the start of the video, it takes a lot of force to overcome the strong force, But when you do, you can create a chain reaction of nuclear reactions to create nuclear weapons. Splendid. Anyways, stemming from that, we also figured out that we can use the atom as a source of energy instead of a weapon for mass destruction, so we began using it for that as well. At the same time, we were realizing that many things were probabilistic in nature, and quantum physics as a field was really kicked off by those like Schrödinger and Einstein. Einstein in particular actually created one of the two most important theories in physics, relativity. If you combine relativity with the field of quantum mechanics, then many physicists believe that you'd actually be able to create a theory of everything. However, to bridge the gap between those two fields, you'd have to solve many more mysteries of physics, like gravity, for example. Gravity is the only force without a force carrier. Some believe that there is a boson out there that would allow gravity to exist, the graviton. What is a boson? It's a subatomic particle. Bosons, along with quarks and leptons, make up the standard model. But there is one subatomic particle that stands out. One that was only just recently discovered in 2012. One that is the ultimate force carrier. This little gray dot. Do you want to know what it is? Just click restart. I'll explain it one last time.